Okay, hello everybody. In this module, we're going to be talking about modern design methods. And in particular, we're going to be looking at how we can use state space models to design a controller when we have access to the states of the system. And then we're going to look at what we can do if we do not have access to the states, and therefore we're going to have to estimate them. Okay, so in this course, we looked at the non-uniqueness of state space representation. We know that the state space representation is not unique. You can choose the states differently and get a different model of the system or different representation of the system. We looked at how to calculate the transfer function from the state space representation. We also solved the discrete time state space equations. And also we looked at the initial conditions and the observability matrix. Now again, what we're going to be looking at here in this module is we're going to be designing a controller using these modern control techniques using the state space representation. Okay, so let's look at the first topic, which is the pole placement by state feedback. And what we're going to be doing, assuming that we have a plan that is described by the state space representation. This is the state space representation we're familiar with. We have the input, U, and we have the output, Y. And we're going to also assume here that we have access to the states. X is the states, so therefore we're assuming we have sensors that we can measure all the states of the system. So if you're measuring a motor, we have a state that will we have a sensor that measures the location or the position. We have a sensor that measures the speed. All the states in the system can be measured and we have access to them. Now what we're going to do, U is the input to this system, and what we're going to be doing is we're going to be having U of k equal to Ks multiplied by X of k plus Ki multiplied by R of k. So we're going to have a feedback of the form U of k is equal to Ks X of k plus Ki multiplied by R of k. If X is n by 1, then U is 1 by 1, and Ks is 1 by n, and Ki is 1 by 1. What does this mean? Let's look at the graph. So this is our state representation, and what we're doing here, we're taking the states, the X of k, we're multiplying it by X by Ks, and then we're taking our input R of k, we're multiplying it by Ki, we're adding these together, and this will be the input for the open loop system. And therefore U of k is going to equal to Ki multiplied by R of k plus Ks multiplied by X of k. So we're feeding back the states, and we have the input R of k multiplied by Ki. Okay, so if you look at the equations for the closed loop system, we have X of k plus 1 equal to A X of k. Originally this was B multiplied by U of k, but now we replace U of k with Ks multiplied by X of k plus Ki multiplied by R of k. Again, U is equal to Ks multiplied by X of k plus Ki multiplied by R of k. Therefore, we can write this as X of k plus 1. If we put the terms together, A plus B multiplied by Ks multiplied by X of k plus B multiplied by Ki multiplied by R of k. Now this is the closed loop state equation. Now if you look at the output is equal to C multiplied by X of k. The output Y is equal to C multiplied by X of k plus D multiplied by U of k. But U of k is equal to Ks multiplied by X of k plus Ki multiplied by R of k. And therefore we can write this, the output, as Y of k equal to C plus D multiplied by Ks multiplied by X of k plus D multiplied by Ki multiplied by R of k. Okay. Now if you look at the closed loop system, with these two equations, is going to have eigenvalues, which are the poles of the system, that now going to be associated with A plus B multiplied by Ks. The closed loop system, the open loop system, the poles are associated with A. Now the closed loop system, the poles are associated with A plus B multiplied by Ks. Now why is that important? Okay, so let's look at a fact that we're going to need in order to understand the importance of this. If we have a single input, single output system, if we establish the matrix P that is equal to B, A multiplied by B, A squared multiplied by B, all the way to A n minus 1 multiplied by B, this matrix that we established, the P matrix, is going to be n by n. Now, if this matrix that we just established is non-singular, which means the determinant is not equal to 0, then we call the pair A and B controllable pair. And therefore, that means we can place the poles arbitrarily at any location by the state feedback. So again, if we establish this matrix P, that is going to be n by n, and if this matrix is non-singular, this means this system is controllable. The matrix AB is controllable, and this means we can place the poles at any location that we want using this state feedback. Let's look at an example. So we have the open loop system, x of k, 0, 1, 3 over 4, negative 1, 0, 1, u of k, and y of k is equal to 1, 0. This is a 2 by 2. And therefore, what are the eigenvalues of the system matrix? If I look at the open loop and calculate the eigenvalues, the determinant of lambda I minus A is going to be lambda, negative 1, negative 3 over 4, lambda plus 1. We calculate the determinant, lambda squared plus lambda minus 3 over 4. If we solve this, we're going to find that we have eigenvalues that are 1/2 and negative 1.5. Is the system stable? No, the system is not stable. Why is the system not stable? Because we have poles that are at 3 over 2. And therefore, or at negative 3 over 2, which means they're outside the unit circle. So my poles, this pole at 1/2 is going to be at the inside the unit circle. It's fine. This pole at negative 3 over 2 is outside the unit circle, and therefore the system is not stable. Okay. Now, for this system, is the system controllable? We are given A, we have B, we have C, and we're going to see if the system is controllable. In order to determine whether it's controllable, we have to create the matrix P, which is going to equal to B, A multiplied by B. And of course, in here, when we calculate this matrix, B, A multiplied by B, we keep going till we establish a 2 by 2, because A is 2 by 2. N is the size of A. So therefore, in this case, we have, let's go back here, we have A that is 2 by 2, therefore P is going to equal to B, A multiplied by B. So B is 0, 1, A multiplied by B, we take the matrix A, we multiply it by the B matrix, and if we do this multiplication, we're going to get the matrix P that is equal to 0, 1, 1, and negative 1. The determinant of this matrix is not equal to 0, and therefore P is non-singular, and therefore we can use state feedback to arbitrarily place the closed loop poles at any location, because this system is controllable. Okay, so in the next part we're going to find the state feedback gain, Ks, required to place the closed loop system poles at z equal to 1/2 and z equal to a 3 over 4. So if based on the specification of the performance or the response, we want our poles to be at 1/2 and 3 over 4, we're going to find the value of Ks that will result in the poles at 1/2 and 3/4. Okay, so we're going to go back to our state equations that we developed here. At the beginning, the state equations, and therefore x of k plus 1 is going to equal to a plus b multiplied by ks, x of k plus b multiplied by ki, r of k. Now the poles of the closed loop system are the same as the eigenvalues of a plus b multiplied by ks. So therefore we need to choose ks so that the eigenvalues of a plus b multiplied by ks are located at z equal to 1/2 and z equal to 3/4. So let's calculate the determinant of zi minus a plus b multiplied by ks, and that is going to be z multiplied by identity minus the a plus b multiplied by ks, and ks is equal to k1 and k2. Now if we multiply these and simplify, we're gonna get, if we calculate the determinant, z squared plus 1 minus k2 multiplied by z minus 3/4 plus k1 equal to 0. So therefore, the desired characteristic equation, this is what the design wants us to meet, is we want z minus 1/2, we want a pole at 1/2 and a pole at 3/4. So therefore z minus 1/2 multiplied by z minus 3/4, this is going to give me a characteristic equation that is z squared minus 5/4z plus 3/8 equal to 0. Now what I currently have with k1 and k2, this is the characteristic equation. If I compare the terms, it means I want 1 minus k2 to equal to negative 5/4, and I want negative 3/4 plus k1 to equal to 3/8. I can solve for k1 and k2, and in this case k1 is going to equal to negative 9/8 and k2 equal to 9/4. And therefore, if you choose these values for k1 and k2 that multiply the state, we're going to be able to place our poles according to the requirements that we had, which is z equal at 1/2 and a pole at 3/4. Okay. Let's look at another example. So in this example, we have the open loop system, x of k plus 1, 2, 0, 0, 1/2, x of k plus 0, 1, u of k. In this case, if I calculate the eigenvalues, the poles, they are at 2 and 1/2. So the system is not stable. Again, we have the pole at 2, which is outside the unit circle, which means the system is unstable. Now let's see if the system is controllable. Before we do the calculation, let's see if we can get some intuition whether we're going to be able to control this system using the state feedback. If I look at the B matrix, the first element is 0. This element is 0. And therefore, this tells me when I calculate the states, x of k plus 1 or x1 of k plus 1 is going to equal to 0 multiplied by x plus 0 multiplied by u of k. So therefore, if I write the state equation for x1, x of k is equal to x1 and x2. x1 of k plus 1 is equal to 2 multiplied by x1 plus 0 multiplied by u of k. And therefore, u of k, which is what we're going to be able to change, has no effect on x1 because it does not show up in this equation here. So again, when we wrote the state equation for x1, x1 is just equal to 2 multiplied by x1, and it does not depend on u of k. And if I look back here, So what this tells me, u of k will have no impact on the state x1. And that tells me, since the x1 is not dependent on u of k, I should not be able to use the pole placement method, because again, the state is not dependent on the input. I can change the value of the input or control the value of the input, but if that state inside the system is not dependent on that input, then I'm not going to be able to control it. Now let's see if the calculation verify our intuition. Okay, so let's check. We're going to establish the matrix P is going to equal to B and A multiplied by B, and this matrix is going to equal to 0, 1, 0, 1 half. Now if we calculate the determinant is equal to 0, which is what we expected. The determinant is equal to 0. This means the system is not controllable, or we cannot use the pole placement method in order to control it. So here we saw two examples. One system is controllable and one system that is not controllable. If the system is controllable, then we can place the pole zeros using the state feedback that we introduced in order to place the poles at any location. Okay, now in this method, in order to apply this method, we're going to have access to all the states of the systems. I have to have sensors that measure all the states in the system, because this is part of the feedback that we're going to be using. I'm using x of k, and I need access to all the states of the system in order to be able to apply this feedback. Now what happens if I do not have access to all these states? In that case, what we can do is we can develop an observer. So in this section, we're going to look at the observer feedback design. Again, if you consider a single input, single output system, this is the open loop state representation. Then if A and B is a controllable pair, then we saw that we can arbitrarily place the poles of the closed loop system using the state feedback u of k, ks, x of k plus ki r of k. Again, as we said, in most cases, we only have access to the output of the system and not the states of the system. And therefore, we need a way to estimate x of k from the measurements of the output and the knowledge of u of k. Y of k, we always have access to the output of the system. I should always be able to measure the output of the system. U of k is the input, so we have access to it. And what we want to do is I want to be able to estimate the state so I can use it in the state feedback, even though I do not have sensors or I do not have access to the actual states in the system. Okay. And this is done by designing an observer or an estimator, the same thing, observer or an estimator. So the idea, this is the observer that I'm going to be designing in order to estimate the states. I'm going to take the output. So this observer is going to take the output that I can measure and the input that I can also measure, and I'm going to get an estimate of the states of the system. Then I can use this estimate in the design of the controller. So in here, this is used to be x of k because I have access to the states of the system. But if I don't have access to the states of the system, I can estimate x of k and use it multiplied by ks and add it to the adder here, and then I can do my state feedback controller. Okay. Now, what we're going to do is we're going to be estimating x of k. Ideally, we want x tilde of k. This is the estimate of x of k. We want it to converge to x of k. So again, ideally, we want to estimate the state as accurately as possible. So therefore, I want x tilde of k to converge to x of k. So we can use the state feedback. U of k in this case is going to be ks multiplied by x tilde plus ki multiplied by r of k. So again, here instead of x of k that I do not have access to, I'm going to use the estimated x of k to do the feedback. Okay. So let's look at the observer state equation. Suppose we have the matrices A, B, C, D describing the open loop system, and they are known. So the matrices A, B, C, and D. We have a system. I model the system. I know exactly what the matrices that represent the system are. Now we're going to consider the estimate of the state. X tilde of k plus 1 is equal to A x tilde of A multiplied by x tilde of k plus B U of k plus L multiplied by y tilde minus y of k. And y tilde is just equal to C multiplied by x tilde. So therefore, what we're doing here, let me go back to this here. What we're doing here is we have this observer. This observer is gonna generate y tilde. I have access to y tilde, I have access to y, and therefore I want to see what conditions will result in x tilde getting a good estimate of the state of the system. Now we have a matrix L that we introduce, and this matrix is of dimension n by 1, and this is called the observer gain. Okay. Now, if x of 0 is equal to x tilde of 0, then we expect that x tilde of k is gonna equal to x of k. And actually, more probably I should have written this as if x tilde of 0 is equal to x of 0, then we expect x tilde of k to equal x of k, because both systems are going to be exactly similar. We're starting with the both of these systems that we had here are going to be exactly the same. This is the plant. I have A, B, C, D of the plant. I have the input. I have the initial conditions. Then if I run this and I run this, they should exactly match. However, what happens is that the initial conditions is seldom known a priori. I might not have access to the initial conditions of the system, and therefore I might start with an error in the estimation of the output. Again, if I have access to initial conditions and I have the model of the system, and the system, I run the model, the output that I should be getting from the model and the output I should be getting from the system should be 100% matching each other. However, I might not have access to the initial conditions, and therefore, if I don't, then my model is going to generate an output, the system is going to generate an output, and there is going to be an error between what my model is generating and what the system is generating. And this error is equal to y tilde minus y of k. This is going to be an error that is going to be greater than 0. However, what we're going to be doing is we're going to be using this error in order to correct for our estimate of x of k. So therefore, we're gonna define the observer error E of k as equal to x of k minus x tilde of k. We want the error to go to 0 as k go to infinity. In the steady state, I want to have an exact estimate of the states, and therefore the error is gonna go, I want the error to go to 0. Okay, so if I look at the error signal between the state estimate and the actual state, E of k is gonna equal to x of k plus 1 minus x tilde of k. X of k is equal to a x of k plus b u of k minus x tilde is gonna equal to a x tilde of k minus b u of k minus L multiplied by c x tilde minus c x of k. I can put the terms together. E of k plus 1 is gonna equal to a plus lc multiplied by x of k minus x tilde. But this is nothing other than the error signal. So E of k plus 1 is equal to a plus L multiplied by c multiplied by E of k. Now if I want the error to go to 0 as k goes to infinity, so I want the steady state error, or this error, to go to 0 as k goes to infinity, we have to make sure that this matrix here, A plus LC, has eigenvalues that are less than 1. Because if the eigenvalues, if the poles of this matrix are inside the unit circle, then they all gonna die out and they're gonna go to 0. And if they go to 0, this means the error is equal to 0, and therefore I have a perfect estimate of the states of my system. Okay. Now we can use another fact, which is if I calculate the matrix Q that we've seen at the beginning of the semester, if I calculate Q that is equal to C multiplied by A all the way to C multiplied by A to n minus 1, if this Q is non-singular, which means the determinant is not equal to 0, then we can arbitrarily place the poles, which are the eigenvalues of A plus LC, by choosing the observer gain L. So I can always, by properly choosing the gain L, I can place the poles of the Q to ensure that the error is gonna go to 0. In this case, we call that the system is observable, which means I can be able to estimate based on observing the output of the system. I can estimate x of k of the system. Okay. Okay, so again, we just introduced this modern communication, modern design methods. We looked at two concepts that the takeaway from this module: the controllability and observability. If the system is controllable, then I can use the state feedback in order to place our poles of my open loop system at any location. And this is how it is done. We take the states, we multiply by constant, we take the input signal, multiply by constant, and we use that as the input of the open loop system. Now the other concept is the observability. The system, what condition is the system observable? Which means I can look at the output, and from looking at the output, I can create an observer that will tell me the states of the system, that will estimate the states of the system. Now, if I have a system that I do not have access to any of this system states, and I want to design a controller for it, what we can do, or what we can do, is that I can design an observer. The observer is going to just take the output of the system and based on the knowledge of the system, estimate the states of the system, and then I can use the estimates of my states in the feedback to design the controller. Now we have the conditions that we have to meet in order to make sure the error of the observer goes to 0 when in the steady state. And if we meet these conditions, if the system is observable, then we should be able to estimate the state of the system and use them in the design of the controller. Thank you.